My name is James Kelly, and this is my overview of Lab 5, Magnetic Braking with Faraday. Purpose. The purpose of this lab is to observe a magnet falling through an aluminum tube and record the time it takes to fall through. Then, to apply Faraday's law in a computational model based on real-life observations. The main physics principles for this lab are the Biot-Savart law, Faraday's law, Newton's second law, Ohm's law, magnetic force on a loop, and the time derivative of magnetic flux on a dipole. All of these equations are critical to developing the computational model that will be later used in the lab. Observations. So upon initial testing, the magnet takes longer to fall through the aluminum tube than it does to fall normally. This implies the aluminum tube is creating some kind of interference with the force of gravity. The results of the experiment model are that it took an average of 1.244 seconds to fall through the aluminum tube, and according to the computational model, it should take 1.188 seconds to fall through the tube. Conditions of the experiment. The system is the magnet, which serves as a magnetic dipole, and the surroundings are the Earth and the aluminum foil tube. The initial conditions are a magnet at rest being affected by only the Earth's magnetic field and Earth's gravity. Assumptions. Air resistance on the falling magnet is negligible, and also, gravity and magnetic force from the aluminum tube are the only forces acting on the magnet. Details of the experiment. First, using a magnetometer on a cell phone, the north pole of the magnet was recorded. Then, using the phone's camera, the magnet was dropped through the aluminum tube 5 times. Using the timestamps of the video, the time it took for each magnet to fall through the tube was recorded. Data from the experimental model. So, the tube itself had a length of 0.3 meters with a width of 0.006 meters. This is the width of the actual aluminum itself. The inner radius of the tube was 0.02 meters, and the radius was 0.032 meters. The magnetic dipole of the magnet was 3.21 ampere meter squared, and the mass of the magnet was 0.025 kilograms, and the average fall time was again 1.244 seconds. Computational model. The computational model was then created using a Python code which calculates the magnetic force on the magnet which counteracts gravity. It calculates the induced current over the full radius of the tube in order to then calculate the magnetic force on the magnet. Here you can see a screenshot of the computational model, starting with the Python code. It establishes some statics, some geometries of the tube, and then some constants of like the mass and the magnetic dipole moment of the Bauer magnet. Then the code will go into calculating the change in magnetic flux over time as the magnet passes through the tube. It will then use this flux to calculate the magnetic force on the magnet based on each ring in the tube, and then be multiplied by the length of the tube. Finally, it'll add up the force of gravity and the magnetic force on the bar magnet, and it'll adjust the net force and then velocity and position based on the net force at each location. Here are the results of the computational model. The computational model found that it took 1.188 seconds to fall through the tube, and it also here is a velocity versus time graph created by the code as well. Discussion. Subtrusive model. Because air resistance was likely negligible, there are no significant discrepancies between the two possible models. One potential source of error would be an incorrect calculation of the magnetic dipole moment. Another source of error could be human error in calculating the time it takes for the magnet to fall through the tube during the real-life model. Conclusions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? If the resistivity of the conductor was reduced as close as possible to zero, the induced current in the tube would be much greater, thus increasing the magnetic force acting on the magnet and slowing it down even more. It may even completely negate the effects of gravity entirely. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, if holes or slots were cut into the tubes, then the induced current in the tube would be much weaker, and the magnet would fall through the tube much faster. Because each ring current relies on the ring being undisturbed, if there were any breakages in the ring currents, that means the current would be less strong. Therefore, the magnetic force would be weaker, and thus gravity would allow the velocity in the negative y direction to change much quicker. Thank you.